We're now going to turn our attention to a case study, the first part of the two-part case study, to demonstrate the key operators we just talked about. Things like create and interval and range and filter and take and do finally and so on and so forth. So everything we've kind of talked about up to this point, we're going to discuss, and we're going to do this in the context of an example that will create large random big integer objects and then asynchronously check to see if they're prime using a background thread from the default parallel thread pool. So this is a really cool example that will demonstrate lots of features that we've talked about thus far, also demonstrating asynchrony in the context of Project Reactor. And it also illustrates how to use mono from runnable, which is just this fun little method we talked about earlier that has a kind of a hook to get something done before, when used in conjunction with the then operator, it's used to do something before everything shuts down. You can find this particular example here in my ex2 folder in the Flux directory on my GitHub repository. So we're now in my ex2 folder in the project called ex2, which demonstrates the examples we've seen from Flux in IntelliJ. So let's start, as always, by taking a look at the entry point into the program. And you can see that we've got two test methods. Test is prime timed, and test is prime async. And both of these things do very interesting asynchronous capabilities and demonstrate features of Project Reactor. We're just going to talk here about test is prime timed, and then we'll talk about test is prime async in part 2. As usual, we register both of those test methods. We then use the async task barrier to run them in the background. They will, in fact, run asynchronously, so we're actually getting our money's worth for the async task barrier. And what that's going to do is start up the tasks, and then it'll wait in the main thread for everything to finish. And then at that point, the program will culminate by printing the number of tests that were passed. So let's go take a look at Flux EX, which is where all the fun begins. And this basically demonstrates a bunch of Project Reactor features to asynchronously perform various Flux operators. And we'll take a look and see what some of those are in just a moment. Let's start by just taking a quick look at some of the fields defined in this class. There's a field called S max value, which is the maximum random number value, which we make at 10 million. We then have the max number of iterations, which is going to be 10. And we're also going to have another field, which will be the lower bound, which is the starting point of the randomly generated big integers. And you can see here that lower bound is going to be S max value, which is 10 million, minus the number of iterations. And we choose those values intentionally. We're trying to generate values in that range to try to induce duplicates. So we want to get some duplicates, and you'll see why we want duplicates as we go through this. The reason we want to have duplicates is we're going to use a very clever technique called memoizing, not memorizing, but memoizing. And that's a way of being able to map candidate primes to their smallest factor if they aren't prime, or 0 if they are prime. And so you can see here that we have the S prime cache field where we make a new concurrent hash map, which maps a prime candidate big integer, such a very large number, to either 0 if indeed it's prime, or its smallest factor if it's not prime. And that's what gets cached. And we do this so that we don't have to keep recomputing the prime calculations every time. We just store them in a map and we look them up, which, if you think about it, if you had lots of duplicates, could be much faster than having to recompute the prime number check each time, because prime numbers take a while to check. A couple more fields we have here. We have one called sRandom, which is a new random number generator. We have something called sleep duration, which is the number of milliseconds to wait for interval, which will be half for sleeping for the Flux interval operator. And so basically, that's just how long we wait between emitting the next value. You'll see how that gets used. It's really cool. And we also have a predicate that only matches odd numbers. You can see this is kind of fun. Look at this. It's a predicate that takes a big integer, and it says, if we mod the current value of the big integer by 2, and that equals 0, then it's even. So we negate it, so it's odd. So what we're doing here is we're only matching odd numbers because we're negating this particular computation. And then the last field we're going to look at here is something that's a function called sGenerate random big integer. And you can see what it does is it's going to make a big integer whose value will start from the lower bound up to but not including a random number which is in the range of 0 to S max iteration. So we're going to generate basically a random big number. And the goal here is to try to get some duplicates if we possibly can. So this particular set of tests takes a while to run, so I'm going to start running it in the background while we look at the implementation. So right now we're just going to look at test is prime timed. And this is going to use the interval operator we talked about to generate random big integers in a background thread, and then we're going to check to see whether or not those values are prime using the other mechanisms we talked about earlier from Project Reactor's Flux class. So as is often our case, we start with a string buffer, and the string buffer is going to keep track of where we want to store the diagnostics to be output. We're then going to make a little callback called log big integer, which is going to write the big integer to the string buffer. You can see all it does is it just goes ahead and calls the print method. The print method is very simple. It just appends the current string into the string buffer, indicating what thread things occurred in. And knowing what thread they occurred in is important, and also knowing what the current time of day is also important. So now what we're going to do is we're going to have a Flux stream, and we're going to say flux.create, and that's going to create a flow of random big integers that are generated at a periodic interval in a background thread. And what we're going to do here is we're going to call a factory method called make timed flux sync, and we'll look at that in a second. What it's going to do is it's going to generate a bunch of random big integers in the background. We'll see how that works. It uses interval. And then what comes out of that will be a stream of numbers, and then we're going to go ahead and do other computations on those using other operators like do on next, map, then, and so on. So we'll first take a look at make timed flux sync. So this is a factory method that bridges the reactive world with the callback style world to emit a time-based flow of random big integers at a periodic interval. So here's how this is going to work. When this thing is called, we're going to basically have it return a consumer to a flux sync of big integers. And here's what this looks like. This is completely crazy syntax. You just have to get used to it. So what we're going to do is we get something called a sync, and a sync is how we are going to pass information from this context back up to the calling context. Remember, the calling context was this other flux stream that's going to manipulate the big integers that we're getting from this flux stream. So it's kind of nested flux streams. And the way this is going to work is we're going to use flux interval, and that's going to generate a long stream starting at 0, and it will do it periodically in a background thread from the scheduler's parallel operator, or from the scheduler's parallel thread pool, let's say that. So you can see here that what this will do is this will generate long, starting at 0, every half a second. Sleep duration was 500 milliseconds, so it's every half second we're going to emit a long. And then we're going to ignore the value. We don't care the value. We just want it pulsed out every half a second. So every half a second of this signal will be emitted. And what we're going to do instead is we're going to use the map operator to generate a random big integer. And here's the generate random big integer. It's just going to create the next big integer in that range. And that will then be filtered so we only allow odd numbers. We don't want even numbers. They couldn't possibly be prime. Why bother even wasting anybody's time? We're going to use odd numbers. And then we're only going to take S max iterations of them. And then the last thing we do, remember that we always need to have some terminal operation to get a flux to do anything interesting. We're going to use subscribe, and we're going to pass in various methods we get from sync. Sync is this flux sync that's used here. And so what we're doing here is we're saying sync next. So if everything goes well, we're going to pass the random big integer up the stream to whoever's downstream. If things go wrong, then we just complete the stream. We just kind of swallow the error. We're like, we're done. We won't get an error here, but if we would, we could log it. In this case, we just ignore it. And then if everything terminates normally, we send the complete signal up the stream using the sync. So at a high level, what we're doing here, this is the great thing about reactive programming, is once you understand what the operators do, you can sort of read it top to bottom without worrying about looping and if statements and so on. We're basically saying every half a second, generate a random big integer, get rid of anything that's even, only take up to S max iterations of them, and then pass them up the stream using the sync mechanism to pass them along to the caller. And here is the caller. The caller was the create factor method. So what we're doing is we're creating these big integers, big random integers, and that's then coming out as a stream. So you can see what comes out of create is a flux of big integers, which have the properties we just talked about, right? They're not even, there's going to be 10 of them, they're random, they're big. We then go ahead and log them so we can see what the results are. That's important for reasons you'll see in a second. We go ahead and then check to see if they're prime. Check if prime does some really, really cool stuff. Check what it does. It goes ahead and it creates a new prime result. We're going to look at prime result in a second because that's very important to understand too. It creates a new prime result, and prime result will be a tuple that contain, or a record that contains the prime candidate, which is whatever number we're checking for primality, and then the results of calling S prime cache compute if absent. Compute if absent is a super cool atomic check then act method that we use as a memoizer cache. And so what this does is compute if absent goes and looks up in the concurrent hash map and says, is there already a value for this prime candidate? If the answer is yes, that means we've seen it before, so it's a duplicate. So it'll just return the current value. However, if there is not a value for that particular key, for that prime candidate in the map, it's then going to call this mapper method, and it's going to go ahead and check to see whether or not the number is prime. And so we have this code that checks to see if a big integer is prime. Obviously, even numbers can't be prime. We know this won't be even because we filtered out even numbers earlier, but this is a more generic is prime method. So we know that even numbers can't be prime, so we check to see if it's prime, or if it's even rather. If it's not even, then we go ahead and check to see if it's got a smallest factor. If it does, we return the smallest factor. If it doesn't, we return big integer 0. So compute if absent is going to either return to us, compute if absent will always return a value which was either already there, in which case we just return it, or we didn't have it, so it gets computed by the mapper method, stored in the hash map under that key, and then returned. So we always get back the result of checking whether something's prime, but we may not always have to check if it's prime if it's been cached before. So these values are stored in prime result. Let's go take a look at prime result. Prime result is a very cool feature that was added in, I believe it was Java 15, and then I think it was kind of finalized in Java 16. So it's a very recent feature. And what it does is it's essentially something called a record. And a record is a data holding value. So unlike an object, you're familiar with objects. Up to this point, up till records were introduced in Java, everything was an object. Objects come with some extra baggage. They come along with an intrinsic lock, and they come along with all the stuff inherited from the object superclass. So they actually have a non-trivial amount of weight. They also have a v-pointer in them because all Java objects have virtual methods, at least could have virtual methods. So a record is like a stripped down data structure. It's kind of like a struct in a language like C, which only holds data. It does not have an intrinsic lock. It doesn't have an intrinsic condition variable. It does not have anything else that would come from the object class, like a v-pointer. It just contains the fields. And the syntax is a little bit wonky. It looks kind of like you're defining a method, but basically these are the two fields, prime candidate and smallest factor, that make up the prime result record. So it's a useful thing to know, especially if you do a lot of data-intensive processing. So we check to see if a number is prime. What will come out of that is a stream of prime results, which we then go ahead and log, so we know what the results are. So we can say things like, we found a non-prime number, we found a prime number, depending on the results. And then the last thing we do is we go ahead and terminate this Flux stream with then, which indicates we're going to get back a null or a mono to void, which, not a null, you get back a mono to a void, which would be an indication to the async task barrier that we're done with our processing. But before that, we call the mono from runnable operator, and we display the results that we've been the diagnostics we've been keeping track of in our string buffer by converting it to a string and then going ahead and displaying it. Okay, so that's the behavior that we're looking at here. That's the code. So let's go ahead and take a look at what we got when we ran the program. And remember, there's two tests. We're just going to look at the one called test is prime time. But I will note something kind of funny. If you take a look back here at the driver program, you see that test is prime time got registered first, followed by test is prime async. But when you look at the results, you'll see that the test is prime async finished first. And the reason for that is that test is prime timed emits the data every half a second, where test is prime async, as we will see in our next part of the case study, just blasts the data out as fast as it can. So this one's going to take longer to run. The second one's going to take longer to run, even though it started first. So what we do is, if you look carefully here, if you look at the numbers, you can see every half a second we have a thread, which is from the parallel thread pool, which is where interval runs, emit a random number that's within a certain range, just shy of 10 million. So you can see that we emit these numbers, and you can also see that we are only going to emit numbers that are odd. We ignore all the even numbers, so you only see odd numbers. And you'll also see some duplicates. So here, we're going to go ahead and when we first emit this number, that gets emitted, and that happens to be a non-prime number. This number actually happens to be a prime number. Here's the prime number again. And of course, what's happening with our memoizer cache is the second time it sees a number, it's not going to go ahead and compute it. It's just going to go ahead and look it up. So it found a couple of these things. So you can see that 9999991 was emitted 3 times, and therefore only the first time was the isPrime method called. The other times it just looked the value up in the memoizer cache. Okay, so that's basically kind of illustrating how the timed approach works. And you'll also notice that all the processing is all done in parallel-1. That's the thread from the parallel thread pool where all the computation occurred. And I mention that because when we take a look at the next example, you'll see that we have one thread that's publishing and one thread that's subscribing. So we'll see how that works when we get to the next example in part 2 of the case study.